Go ahead, please.
Problem. No problem. Glad to see you. And just interrupt me as soon as my time is on.
Thanks.
Hi, Jorge. Thanks for the invitation. I'm very happy to talk in this very nice conference, which covers a large spectrum, a lot of nice talks. So look forward to the rest. The topic is really, in a way, technical, which says from the title about the diagrammatics and Feynman calculus for gravitational modes in certain class of theories. And let me just set the background, which is very general. It belongs to the class of studying strings from field theory, large N field theory, which really goes back to 't in 1974. It has been greatly enhanced by concentration on CFTs, ADS CFT, but it is really an old subject of large N, gravity or strings from large N. And while many higher dimensional theories were studied, in particular N=4 super Young mills belong to this class, and the 10-dimensional string belongs to the class. It is interesting that lately, and especially in relation to understanding gravity, understanding space-time, understanding precisely the topics that were discussed in the previous talks, quantum black holes, it came to lower dimension, meaning that there is a big concentration on understanding lower dimensional models. And you will see that even though they are lower dimensional, they contain possibly answers to all those questions. So, and they are not as trivial as you might expect. So those are the topics which are really studied by a huge number of people. So it's maybe 1/3 of the very theoretical community that is studying these topics. And these simple models for a focus. In 1990, those were the matrix models. And the matrix models related to 2D or less than 2D strings. And that was a very full correspondence between 1D matrix models, quantum mechanics, large N, and 2D non-critical strings. That model still might be, and some people still bet that this might be the best model, while we can understand all the above questions. Nevertheless, there has been a new popular model, which came from condensed matter. It's fermionic. It's the so-called SYK, Jevicki model, which has been studied especially in the last three years. I'll describe our latest talk with Shumit Das, Ghosh, Kenta Suzuki on how to do perturbation theory in these models, and you will see why. And this reference will have all the previous references. So there is a huge number of papers, and whoever is interested will be able to look at those. But just since I have limited time, it obviously will not be a technical talk. Then who is interested or intrigued might look at some of the papers. So the model is due to Sachdev and Ye in 1993 for totally condensed matter studies. It was understood, the physics was understood by Kitaev in 15. And after that, there was a big jump in activity because Kitaev mentioned that it has something to do with anti-de Sitter space and gravity in 2 dimension, and thereby a large activity after that. So the model is just the model of Majorana fermions, which are quantum mechanical, anti-commutation relations, quartic interaction in the Hamiltonian, but there is a tensor index random coupling, which is averaged over typical condensed matter system. This would be random average. And in that sense, it differs from other models that we have studied in this large N string duality. And the physical meaning in that context of this random coupling and its averaging is not quite understood yet. But nevertheless, people have studied this model a lot. And it has been solved in large N. The reason, the way it has been solved is through very similar techniques of how the QCD2, the 't Hooft model of large N, was solved. And in that case, one introduces the physics was given by confined quarks into mesons. So that's the meson model of 't Hooft, and this is nothing but a close relative of that. So the main vehicle of understanding the solution, or even doing the solution, and you will see going toward space-time and gravity, will be just this bilocal field, which is an invariant under Sn, and it will be able to encapsulate the large N physics of the model. And the best way that is done, and that is how this is studied, is through an effective action, which I call collective action. The effective action has three terms. It has the old terms from the Lagrangian itself, which is this kinetic term here. And after you integrate out the random interaction, you get a quartic term, or in terms of the bilocal, which would be an 8-power term in terms of fermion. And then there is an extra large N term that is the entropy, or due to this change from large number of N variables to just the bilocal. And this Lagrangian, it obviously tells you all the physics you will want to know about the model. Looks misleadingly simple. This trace log is with a star product of this bilocal, so that tells you a little bit more. It sums up the Schwinger-Dyson equation solutions. So the partition function can be exactly calculated if you do in large term, therefore is dictated by this action. And you'll find a stationary point, study that, and then do 1/n corrections. And that has been a very, very standard way. What happens in this study is that you will soon see, instead of the bilocal, you already see a two-dimensional space-time, just that it's not very visible. And I'll make a comment on how to picture the transition from this bilocal to the actual ADS space-time. That's a non-trivial question. There's some answers to that. But first, some properties of the models which will explain why it is so much studied. It has obviously a dimensional full parameter J, which can be taken to infinity to go to the infrared critical point. And you get a critical theory. And it is only solvable in that critical point. It is not solvable for general J. But at the critical point, it becomes a conformally scale invariant theory, as it always happens with the critical theory. But there is one special thing which happens for this model, and I'm not totally sure to give you an answer why it happens. Besides the scale and conformal, there is a larger symmetry, the parameterization of time. So there is a Virasoro symmetry of reparametrizing time as described it turns out that this trace log, which is a non-trivial quantum effect, and this quartic interaction are both invariant under this space-time reparameterization. So in a way, this feature, which was first mentioned by Kitaev, is the secret of why this model has attracted so much interaction. We do not have that, even though we study large N models, and they are related to dual theories, they are related to strings and so on. Very seldom do we run into seeing reparameterization symmetry right in that CFT. And this is one place, I'm not totally sure I know other places. So that, in a way, points to why this is so central. At this point now, after that observation, it becomes technical. There is that symmetry, reparameterization symmetry, that's obviously a big problem for doing perturbation expansion. The propagator doesn't exist. It has zero modes. And all that that is compensated by understanding that there is some physics going on, that there is a collective Goldstone mode, which becomes dynamical. And one of the central topics, which I would then call topic number 1, and we'll go to topic number 2 and 3, is extracting that Goldstone mode. And this is really equivalent to extracting dynamical gravity from a CFT in explicit terms, not in the sense of comparing correlation functions where the way it is usually done in ADS CFT, but the system is equal. You will be able to identify this dynamical mode. It will be called the Schwarzian mode. And the precise identification and the derivation of the dynamics of the mode is quite non-trivial. So we have done it in this paper with Suzuki. Kitaev and Su have done it similarly. Baldacena and Stamford have done it in the linearized approximation. But the nonlinear theory, which is written down here with an action for a dynamical quantum mechanical mode, is non-trivial. Even in that large N limit, it comes because of regularization or renormalization. It comes because of some surface terms, which then require a short distance expansion. And it starts to remind you of features which people who know gravity, that's how things happen in gravity. That's how energy comes about. The coefficient is N, and that relates to Newton's coupling, gravitational coupling. But the absolute coefficient is even not calculable analytically, so it's done numerically. This also tells you the simple model, which we started from, actually is fairly complicated. Even in the large N limit, we cannot solve it analytically. At some features, one had to do numerically, particularly this coupling constant alpha, which is basically the gravitational coupling constant. I think I emphasized that enough, except the following fact, which is really the reason for the duality. And this is really an observation that two-dimensional Jevicki-Teitelbaum gravity is topological, no degrees of freedom. It would only have a boundary quantum mechanical degree of freedom, which would be the time at the boundary being dynamical. And the value of that coupling is the value of the dilaton at the boundary. And this also takes the same form of the Schwarzian action, and that has been probably known. But now this is equal, and that is why we say that we have recovered gravity or emergent gravity from this CFT in a very explicit terms, not as a comparison. This is the same action. You can couple ADS to JT gravity to matter and study that, and that has been a focus of recent studies in respect to black holes and entropy, islands and supposedly a great progress has been done just by studies in pure gravity. I might make only one comment. It obviously should be studied in a fully fundamental or quantum mechanically correct theory of gravity. So SYK is such a candidate. Why not study it in SYK? It's a bit complicated. It's much simpler to take JT gravity coupled with matter. What's the shortcoming? Do you solve all the problems? Do you need string theory? Do you need any fundamental theory to solve all the problems of black holes, or those were solved by people who, the many papers written this year? No, the answer is they are not solved. The answers which they get are infinite. So apart from an infinity which they drop, if you are willing to drop the infinity, then you don't need a fundamental model. If you are willing to drop the infinity, if you say I will not drop the infinity, I like to understand and get a finite result, then you might want to obviously study the fundamental model. So that is quite understandable. So this fundamental, what I call the fundamental model, the SYK model, which is quantum mechanically renormalizable, finite. It will give finite results for anything, much like the 2D string model would be, which is another competitor to fundamental model, which includes gravity, and it makes quantum mechanical sense. You study, so the spectrum is quite surprising of the model. I will be very quick with this spectrum. After you study fluctuations and solve for the spectrum, you essentially get an infinite number of massive fields. In addition to that mode, which I already spent a fair amount of time, the so-called Schwarzian mode, which is gravity. This would be really matter. Infinite number with certain masses which are quantized according to a certain formula which was found. There is no insight why this formula. This is not a string of any kind, or maybe this is some kind of massive string. It has been not understood what would this correspond to, what the physics of this mass is. But therefore, the matter part of that bilocal action would be, which itself was infinitely non-polynomial, and now it will be infinitely non-polynomial in derivatives also, not only in the powers of the field. So maybe this is just the quadratic approximation of the bilocal action, but it has infinite number of derivatives. At this point, you realize that maybe is the reason for why I said the model is fairly complicated. And in a way, it's remarkable. You have this n Majorana fermions with quartic couplings in one dimension, and it brings you to this point that we say that that action is equal to this infinite number of massive fields in ADS. These fields actually can be packaged as Kaluza-Klein. So you even have not only a 2D picture, but a 3D picture. So there is some very interesting 2D matter theory with infinite number of Kaluza-Klein fields coupled to gravity. Apart from this linearized approximation where we can see how it looks like, the nonlinear terms are not recognizable. We cannot say this is 3D gravity compactified along certain line. We do not have we have the exact bilocal description, but we do not have the exact.
Antal, I'm sorry, I see you have 21 slides and you're on slide 12, is that right?
Yes. And I have how much time?
We're on -5, more or less.
Oh, did you try to stop me yet?
No. I was trying to to let you go. I didn't know how many slides slides you would have. So,
okay, this probably puts the whatever you wanted to hear. Maybe that this would be sufficient. The rest is technical, and in fact, that would be this is summary number one, and then we go to the technical part. The technical part you really don't want to hear. There were 2 papers on developing the full interactions of this Schwarzian world with matter, and one is our paper, another is a paper by Kitaev and Su. We agree in methodology, we probably disagree on some details, which tells you that the details are fairly complicated of how all the interactions look like in this theory. And I think in this paper we have settled that. So just to conclude, there is a set of vertices and Feynman rules for the theory, which we have worked hard to produce. And then the conclusion is that we have this model whose total physical spectrum is known. It is gravity with matter. It's a very interesting model. Interactions are completely known, though fairly complicated. It obviously is a promising model, exact quantum model for gravity, but we don't really know what is it. Is it a string? Is it higher spin? Well, very, very open, interesting question. Thank you very much.
okay, thanks a lot. So, on behalf of everybody, let's see if there are questions.
I have some, if you like.
Yes, please.
Okay. Hi, Joachim.
Yes, one simple question. I wanted to know what is this number Q, if that's a generalization of the model coming from solid state. And the second question, just to use the same possibility, that model you have in the larger limit will exhibit different phases, because a matrix model, you can choose different phases according to the number, for instance, of cuts you have there in the distribution of eigenvalues. Here, could happen the same?
This is in one phase, really, and only if you add extra terms, like some extra couplings, you get different phases.
Okay.
Okay, but the number Q is trivial. It says, obviously, you can generalize this to not 4 fermions. There is nothing special for 4 fermions coupled to a tensor, but Q is the number. So 1, 2, 3, Q. And Q equal 2 would be a trivially solvable model, because it's quadratic in fermions.
Okay, thanks.
Could I ask a question?
Please.
Okay.
Hello. Could you comment more about the breaking of the diffeomorphism invariance to SL2R? I mean, in a sense, the Goldstone character.
That's right. So in a sense, this diffeomorphism invariant is not broken in this theory, because it somehow becomes dynamical gravity coupled to matter, and therefore it is preserved. This is a theory with diffeomorphism invariance.
But the Schwarzian has only SL2 invariance.
No, the Schwarzian, you can change time into any function of time, and it keeps the shape. No?
No, I don't think so. You will have maybe asymptotic symmetry that will be diffeomorphism invariant, but the global symmetries of the Schwarzian is as SL2R.
I see. So, and this is a theory only of time. But you see,
yes.
This is the topological boundary value of JT gravity, which certainly has that symmetry, you know.
Yes, but the Schwarzian not.
And the Schwarzian doesn't. That's okay. So I understand, yes.
Okay.